Everyone can hear me at the back? No. You're not at the back.
I actually did. I'm sure. Can you read his handwriting? Rotation. Move the M-U-T-A-R-O.
Anybody want this?
Alright, so we were doing alpha and beta glucose, and that's true for all monosaccharides, because the aldehyde can react with alcohol, so it can react with any of these alcohol groups of the carbohydrate. If it reacts at the fifth carbon, then it gives a 6-membered ring, and that's why that's the most common one. 6-membered ring is most stable.
What's the word on top?
Muta rotation. So this is called a Priernose ring, which means 6-membered ring. So most of the carbohydrates exist as the Priernose ring. That happened because it forms a ring, but then it is in equilibrium, it can go back to the linear form. And after it goes back to the linear form, it can again form a circle. And every time it forms a circle, it can give the OH here either pointing down or pointing up. So this will be the beta glucose. So these three are in equilibrium, of which the linear form is present in extremely small amount. But in order to go from the alpha to the beta, it has to go through the linear form. Or going from the beta to the alpha, it will go through the linear form. If you have a pure alpha, you can crystallize these things and you can buy the pure alpha glucose. You take that and you dissolve in water. This will be a stereoisomer that has an optical activity, so it will have a certain optical activity, which is also written as alpha. So that's optical activity. And in the same way, the beta will also have a certain optical activity. As you know, optical activity is a property of the compound, just like melting point, boiling point, so optical activity is a property. So if it is a mixture of the two all the time, whether you start with the alpha, as soon as you dissolve in water, some of it goes to this and then some of it goes to that. Yes?
Beta has optical activity too.
Yes.
Is it alpha still? What is that alpha?
It's called alpha.
Okay.
Don't get confused by that term. This alpha and that alpha is not related.
And also, what percent you said did they each exist in? You said it doesn't usually exist as linear?
Yes, small amount,
Small amount.
less than 1%. But it has to go through the linear to the other side.
Okay.
So there will be a certain percentage of this and this in solution. The linear is a very tiny amount. And from your organic chemistry, you know that the relative percentage of two things in equilibrium depend on their energy. Whichever is more stable is present in greater amount. The beta is more stable than the alpha, so this is present in more amount. Let's say it's present about 63%, and this is about 37%. that is related to its energy. So every carbohydrate will exist as a mixture of the alpha and the beta in a certain proportion depending on their stability. So we are not going into the math of it, but the alpha will have a certain rotation of optical light. Beta has a rotation of the light, and the average of that, when it is a mixture, this multiplied by its percentage, and the optical rotation of this multiplied by its percentage gives the final rotation. So every time you have a sugar in solution, it will be a mixture of alpha and beta. It doesn't matter which one you started with. If you started with alpha, it will gradually become alpha and beta in that fixed proportion. In this case, let's say 64 to 36. So the optical activity, again, whatever is the optical activity of this one, it will start with that. As soon as it dissolves in water, you measure the activity, then you find it is changing because it is equilibrating with that one, and then eventually comes to a certain fixed value. So that property is called mutual rotation. Because we are not doing any math regarding this, it's very easy to calculate also what will be the final optical activity, but the concept here is that it is a mixture of two, and so it will be a weighted average of the two. That will be the final optical rotation. So what we get from this, we are not studying optical activity, but what we get from this is that the alpha and the beta are in equilibrium when they go through the linear one. And the linear one is an aldehyde. Aldehydes are reducing agents, so this is easily oxidized. So all the tests for glucose or tests for any sugars that you do, you are actually testing the linear one, because this is easily oxidized, and so when you oxidize it by whatever method, you see what is the amount of reaction you got. That tells you how much glucose you have, because the linear form comes from this. Whether you have the alpha or the beta or a mixture of the two, it eventually goes to the linear form, and that's the one that gets oxidized, so eventually you get everything oxidized. Even though at any given time it's a small amount. And that way, if you also have a ketose, like fructose will also have a certain equilibrium with the corresponding aldose. That means it will also go through the aldehyde form, and so fructose will also give you a test depending on what type of reaction you're doing.
Yes. That's as easily oxidized?
The aldehydes are easily oxidized, yes.
That says optical activity.
No, at the top, the one above CHO.
Okay, yeah.
This is easily oxidized, and so these sugars are called reducing sugars. Yes?
Does fructose form a different kind of ring structure?
Yes, we are going to do that, yes. So, so this is a reducing sugar because it goes to the aldehyde, but how do you know just from the structure? You don't really have to draw all these to know that it is a reducing sugar. You know a reducing sugar if it has a anomeric OH. So anomeric OH makes it a reducing sugar for this reason, and you recognize the anomeric OH, as I mentioned last class. This is the only carbon that is linked to two oxygens. And if you have that OH, that is a reducing sugar. So all sugars are not reducing sugars, as we will see, because they don't have that anomeric OH. For example, sucrose is not. We will talk about that in a few minutes. Now, someone asked about fructose. So fructose will again have a ketone group at carbon 2. So I'm going to erase this and draw the keto form. So to draw the keto form, all you do is put the double bond here. And now again it can form a ring, but it will form a ring at carbon 2 and not at carbon 1. So instead of a 6-membered ring, you get a 5-membered ring. and this one. So you get a 5-membered ring, and this is the OH is down, so this is alpha, and if the OH is up, that's the beta. I'm not drawing the other two OH groups. So when you have a 5-membered ring like this, this is called a furanose. So glucose exists as a pyranose, and this is a furanose or a 5-membered ring. And once again, it's easy to tell which one is the anomeric carbon or the anomeric OH. So this carbon is attached to this oxygen and this oxygen, so this is the anomeric carbon. And again, that can be reduced. Anything that has an anomeric OH can be reduced because it goes to the linear form again. All right, so these are the two main sugars that we will need to know. Now, as you know from organic chemistry, that these are not the actual structure of the sugars because they are planar structure. These are drawn as planar structure, and when you do that, these are called the Haworth projection. The actual structure, as you know from cyclohexane, is a chair structure. So sugars also exist as chair structures, which organic chemists like more. But as a pharmacist, you will mostly find it drawn this way. But just to give you one example.
Really?
So this will be your glucose, which can exist like this, or this in the flip chair structure. And for beta glucose, it's easy to remember. The beta glucose is the only 6-membered carbohydrate that has all the OH groups in equatorial position. So you just draw these in equatorial position, OH here, OH here. So this is beta glucose as opposed to alpha glucose, which is different at carbon 1, that means this OH is down. So alpha glucose has one axial OH, and as you know, axial groups make it less stable, and that explains why you have more of beta compared to alpha. Beta is 63% and this is 37%, because this is the one that has everything in equatorial position, so most stable. And so beta glucose is the most common sugar in nature, because out of the 16 stereoisomers of glucose, this is the only one that has all the OH groups in equatorial position, and nature also found that out, of course, and that's why it makes beta glucose in the maximum amount. Now, as I said, in the, most of the medical books, pharmacy, it's always drawn as the Haworth projection, so most of the time we will be doing it that way. Now, this again is the anomeric OH. This is the one that can be easily reduced. This is also the one that can react with another alcohol. So if you take, let's take only the beta one and react it with methanol. So this reaction will require temperature and acid, and then you can replace the OH with a CH3. I'm not drawing the other OH groups. And this is in one direction only, it doesn't go back. So what will be the name of this? This is beta glucose, so this is beta metal glucoside. So you can have alpha metal glucoside. If the alpha glucose reacts with methanol, it gives you alpha metal glucoside. The beta reacts with this beta metal glucoside, and that is a fixed structure. It doesn't equilibrate and go back to the other form. Now, of course, this reaction is not relevant for us in this course, but anything that has OH groups can react. Methanol can react, or anything else that has OH group can react. Yes.
We don't need to know that.
You need to know more complicated than this. This is coming now.
Like,
So anything that has an OH will react this way to give the same kind of bond. And what has OH? Carbohydrates has lots of OH. So instead of a methanol, you can use another carbohydrate molecule, and that will react. Which OH of carbohydrate will react? It has 1, 2, 3, 4, 5 OH groups. Any one of them can react. So that gives you multiple products, and that's what makes it complicated. So you can have a disaccharide which provides the other OH. So let me write that. So let's say glucose, you can write it this way also. So this is the beta OH. I'm not writing the other groups, and that can react with, or let me write that. So if it reacts with another glucose, so here is another glucose. So which OH will it react with? It can react with any of them, and all of them do exist. Some exist more, some exist less. So this OH can form a glucoside linkage with another OH, either this one or this one or this one or this one. The most common ones are at 4 and at 6. So if it reacts with the number 4 carbon, so I'm going to, here's the top part. If it reacts at 4, then the structure will be like this. This will be joined to this carbon. Right, so this beta glucose is linked to C4 of another glucose. So this link is called a beta 1,4 glycosidic linkage. So this is a disaccharide in which this is glucose, this is glucose. The first glucose is in beta structure, and it is linked to the carbon 4 of the second glucose. So you write those, what are the sugars on this side, on the first and the second one. So this will be the name of this molecule, glucose alpha 1 or beta 1,4 glucose. In the same way, if it was alpha, then it will be glucose alpha 1,4 glucose. Alright, so this way you can have many disaccharides possible, but some of them exist more than others. For example, you can have maltose, isomaltose, lactose. So we are not going to, you don't have to memorize all those names, but one that comes up again and again in the pharmacy when it's related to diseases is lactose. Right, so everyone understands why lactose is important, because some people cannot digest lactose because they don't have the right enzyme to do that, and so that gives rise to problems. So what is lactose? It is galactose beta alpha 1,4 glucose. So you need to know the structure of galactose, and remember last class I mentioned that galactose is different from glucose at 1 carbon, which is carbon 4. So if you look at this molecule as it is drawn, I just chose a random one to be beta linked to 4 position. You can have the alpha linked to 4, or you can have the alpha linked to carbon 6. In any one of them, as I mentioned, 4 and 6 are the most common ones where the bonds take place. So in this sugar, you have a anomeric OH, which I'm writing like this. That means it is again a mixture of alpha and beta. This one doesn't go back. Once it forms a glycosidic linkage, this is always beta because you started with the beta. It cannot be oxidized easily or reduced because it doesn't have the OH here. It is in the glycosidic bond. So this end of the molecule is called non-reducing, and this end of the molecule is called reducing end, because it has this anomeric OH which can be reduced. So once again, when this equilibrates, this sugar will not become the linear chain because it is not, doesn't have the anomeric OH, whereas this sugar will go up to the linear and then the beta and then the alpha. And that's what makes it a reducing sugar also. So this way, instead of 2 sugars, if you have multiple sugars to make a polysaccharide, so if you have, let's say, glucose linked one after another, and that's what is starch. Starch is alpha glucose, alpha 1,4 glucose. Glucose, alpha 1,4 glucose, repeated many times, is starch. And so is glycogen, which is animal form of the sugar stored. Starch is the plant form. So in this starch molecule, this end of the molecule is non-reducing. This end of the molecule is reducing because as you keep adding more and more sugars, the last one will still have the anomeric OH, and so it will be reducing. So every polysaccharide has a reducing end and a non-reducing end. Now, as I said, the glycosidic bond can happen at carbon 4, it can happen at carbon 6, or at carbon 3, and it can also happen in both places. So each of these sugars will also have other OH groups that can also form another glycosidic linkage. So you may have a chain of sugars like this, and then here you may have another chain forming like this. Because this every sugar has other OH groups, and if this is linked to the other as let's say 1 and 4, and there is a 6 here, so this will be 1, 6. Alpha or beta doesn't matter, both kinds of polymers exist. So you can have 1, 4 in this direction and 1, 6 branch, and then again all these are 1, 4. And that's what starch is also. Starch is a branched polymer. Starch consists of 2 polymers. One is called amylose, which is linear, and amylopectin, which is branched. So if it is linear, obviously you have to mention what kind of bond it is, and the bond is glucose, alpha 1,4 glucose. And this is repeated many times, usually about 6,000 or more times to make one polymer of starch. And amylopectin is also the same. with occasional branches. That means some of the sugars will have alpha 1,6 branches. And the percentage of branches is about 4%. That means 4% of the sugars will have 2 glycosidic bonds. Like this sugar has 2 glycosidic bonds. So 4% means 1 in 25. So approximately, sugars don't have a fixed molecular weight or fixed formula. So it's average number 1 in 25. It can be 26 or 28 or 30. Yes.
What is written? Like above 4%?
Alpha 1,6 branches. As I said, sugars have many OH groups. So this sugar is linked to this one from carbon 1 to carbon 4. That's why the main chain is 1,4. And the branch of that this point can be linked to carbon 1 to carbon 6 of that. Yes.
Is amylose and starch are the same?
Yes, the starch consists of amylose and amylopectin. So 2 polymers present in starch. So amylose is a linear polymer with only alpha 1,4 linked chains. Amylopectin has about 4% branches. That means 1 in 25 glucose will have a alpha 1,6 branch. So that means carbon 1 of this is linked to carbon 6 of this one. So every time you form a branch, remember this is the non-reducing end, this is the reducing end, and then again this is a non-reducing end. So for every branch you are increasing the number of non-reducing ends. So if you draw the structure of starch like this with all the branches, every time you are starting a branch, you have started this chain as a non-reducing end, and this is a reducing end. Every time you are starting a branch, then this becomes another non-reducing end, this becomes another non-reducing end. So there will be numerous non-reducing end depending on the number of branches. And there will be only one reducing end. That's where the first glucose started, that has only anomeric OH. And why are we studying starch in relation to human activity? For 2 reasons. One is starch is your food, you need to digest it. And the more important reason is that we also have a form of polysaccharide stored which has exactly the same structure as starch, and that is called glycogen. So glycogen is our form of stored carbohydrate. So I'm going to release all this. So glycogen is the stored polysaccharide. It is stored in the liver and the muscles. The muscles stored it for themselves. Muscles are selfish organs. They just use whatever they have for itself. Liver works for the whole body. So when liver stores glycogen, it supplies glucose to the whole body. Muscles use it for muscle contraction when you need energy. And the structure of glycogen is similar to glycopeptine. That means it has alpha 1,4 linkage and alpha 1,6 branches. The 2 differences is from starch is that larger than starch. In size, so there is no fixed formula, but it is much bigger polymer than starch. And secondly, it has more branches. It has about 10% branches. That means 1 in 10 sugar or every 10 sugar is likely to be a branch. Again, there is no fixed formula. It can be 10, it can be 12 or 8. But approximately every 10 sugar is a branch point in glycogen. Yes?
The What does that say for one?
Larger than starch in size, number of sugar, number of glucose per molecule. As I said, starch is about 6,000, this will be more than 10, 15,000. Now in this structure I have shown that for every polymer of glycogen or glycopeptide, you have one reducing end and multiple non-reducing ends. And that also is not completely correct because that one reducing end also doesn't really exist. Because when glycogen is first made, the first bond between two glucose units is difficult to form. There is no enzyme that takes glucose unit and joins them. The enzyme that joins them is adding a glucose unit to an already existing polymer. So you need an existing polymer to add more glucose to it. We cannot just start a polymerization between two glucose. So how does it start then? It starts on a protein. There is a protein called glycogenin that adds more glucose to it to make the glycogen. That is, this reducing end, which I wrote here, also doesn't exist because it actually started with a protein and not with a sugar. So in reality, then glycogen has only non-reducing end, and whatever, if there was supposed to be one, that one also doesn't exist for the reducing end. And all that is important because first of all, why do we store glycogen? Why do we store anything in a polymer form? In order to make a polymer, you need energy. As I said, whenever you form a bond between two units, whether it is sugar, protein, or whatever, you need energy. So the cell or your body is using the energy to form these bonds, and when you digest it, let's say you eat starch, it has this energy in the bonds, and when you digest it with the enzyme called amylase, which breaks down the amylose bonds, that energy is lost as heat energy. So what is the purpose of investing energy into the molecule if that is going to be lost as heat energy when you digest it? So there are a couple of reasons for that. Why do we store as polymer? Because we cannot store as monomers. The monomers, if you have 100 molar monomer, that won't be soluble, right? You can have a certain number of glucose units dissolved in water. Everything has a solubility problem. So you cannot have a couple of molar glucose, but you can put 10,000 molecules of glucose, make a polymer, and it can be stored that way. So it is more efficient to store. Even if it is soluble at a high concentration, that will increase the osmotic pressure. And the cell will basically die because of the osmotic pressure. So you don't have any biochemical present in more than a millimolar or a couple of millimolar range. That's the usual concentration of most biomolecules because the Km of most of the enzymes are in the millimolar range. And as we saw before, the enzyme is most active at around Km value, which means that is the concentration of most biochemicals in the cell, around a couple of millimolar, 5, 10, 15, 20, like that. But nothing in the molar range except water. So that's one reason that you store them is the solubility and other factors related to solubility. And secondly, the energy that is invested in forming the bond, all these glycosidic bonds need energy, and that energy is actually not wasted. It may appear to be wasted in digestion. That's the only time that you break that bond and not gain anything from it. So the energy is lost as heat energy. As soon as you have everything in your system, other than the digestive system, which is really outside the body, the cell is very careful about not wasting energy. Every reaction is very efficient in energy. So if you have a glucose-glucose bond, there is energy invested in this, and then the cell will actually use this energy to form another bond. Nothing is really wasted just by hydrolyzing it. So none of these compounds are really simply hydrolyzed, because if you hydrolyze it, it will just lose that energy. So that's why most of these things that are stored are stored as polymers. And of course, storage is only for the carbohydrates. Proteins are not stored. Right? If you have excess protein in your diet, that is not stored in the body. Your body makes protein that it needs. Otherwise, every excess protein that you eat is converted to either carbohydrate and then converted to fat. So fat is stored, but fat is not a polymer. So this question only applies for carbohydrates, which are polymers and stored as polymers. Because of these reasons that the energy is not really wasted, it is used for other reactions when you break this bond and then the solubility. So if you have a glycogen molecule like this in the, let's say in the muscles, and when you need it, when you need energy, when you need, let's say your muscles suddenly need energy to perform, so you need glucose. So this needs to be broken down to glucose. And the enzyme that breaks it down is called glycogen phosphorylase. Glycogen phosphorylase breaks down glucose from glycogen at the non-reducing end. So this enzyme has a specificity for the non-reducing end, so it will break down this glucose, then this one. So this way it will break down this glucose only from the non-reducing ends. So more non-reducing ends you have, faster you get your glucose, right? So when you are running a 100-meter race and you just want sudden energy, you want the glucose to be released as quickly as possible. And so it is advantageous for glycogen to have many branches, because every branch means one more non-reducing end, because that's where the glycogen phosphorylase works. So that gives you glucose phosphate plus glycogen with one glucose less. So it's gradually removing one glucose at a time, and the rate at which it does that tells how fast you can run. When the glycogen phosphorylase works, as you see here, it's not wasting energy. There is energy in this bond between the glucose. When this glucose is removed, it's putting a phosphate on it. That means the energy of this bond is now used to form a bond to phosphate. And the whole idea of all metabolism, it has to do with energy someplace or other. And for example, you need glucose to get ATP. That means you need to form a bond with phosphate. And the first bond is already formed without investing in any energy, because the energy was already invested when making the glycogen. So to make the glycogen, you have already invested energy to form this bond, and that bond is not, energy is not wasted. It is used to form a bond between the glucose and the phosphate. So you are having a fresh start with one phosphate extra. That means that will make you one ATP extra. So secondly, then as more non-reducing branches that you have, more faster you will release your glucose. And this enzyme actually works, and it stops here about 4 units from here. So it will remove all these glucose till it comes close to the branch. So all these branches will actually stop about 4 units from the branch point. That is true for digestion of starch also. The enzyme, when it digests quickly up to that point and branch, and then another enzyme comes in and takes care of the branches, and then you get more glucose form. So that will be called the debranching enzyme. So from here, from this remaining glycogen, you need a debranching enzyme. So the debranching enzyme will remove these remaining glucose and put it on the adjacent branch. So that way you have a longer branch now, and you can make more glucose. So that is a slower process. This is the faster enzyme. This is the slower enzyme. So if you are an athlete and you're running 100 meters, you know that you can run that in 10 seconds. The next 100 you cannot run in 10 seconds, it will take you much longer. Because that's where the glycogen phosphorylase stops. It stops at the branch points about 4 glucose in it, and the next enzyme has to come in, that's the slower enzyme. So you cannot keep running at the same speed throughout. If someone had a question, yes? De-branching enzyme.
Grinding or de-branching?
Branching.
So technically then the de-branching enzyme will remove 4 bases. So let's say after glycogen phosphorylase has removed the glucose, what remains is about 4 here and 4 here. So every branch, wherever you have a branch, there will be 4 remaining. And then the enzyme cannot function anymore till the next enzyme, which is a de-branching enzyme, comes. And what it does is it takes these and puts it on top of this one. So what you get then is this one with only 1 glucose left, and this one will have 7 glucose left. So because it takes 3 and put it on top of this 4. So it becomes 7. So then again glycogen phosphorylase can remove this up to 4 again. So this way the process continues, but the process becomes slower because every time it comes to the branch point, the de-branching enzyme has to remove more glucose and increase the length of the branch. So the process eventually will go all the way to the last glucose and give you energy, but that process will be slow. And you don't really have a whole lot of glycogen stored in the body. How much glycogen do you actually have stored in the body? You have enough to last for only 1 day. So we don't really store a whole lot of carbohydrate, only for 1 day. And after, if you are fasting for more than a day, you don't really have any glycogen left. So now you are depending on lipids. And then if you don't have lipids, you are depending on protein. The protein starts to break down, the lipids are used. But the immediate energy comes from glycogen, which you store only enough for lasting 24 hours. All right, so we will stop here. I mentioned we will have the quiz on 21st. That means this Monday, first, same way, about 8 questions, 10 minutes.